Okay.
Start, please.
Okay, thank you. Hello, everyone. Welcome to the last conference of this Congress, Core 21. I would like to introduce to our keynote speaker, Geoffrey West. Geoffrey West is a theoretical physicist whose primary interest has been in fundamental questions and cosmological implications. West served as Santa Fe Institute president from 2005. Prior to joining to Santa Fe Institute as a distinguished professor in 2003, he was leader and founder of the High Energy Physics Group at Los Alamos National Laboratory, where he is one of only approximately 10 senior fellows. So welcome, Dr. West, and you can start when you are ready.
Okay, well, thank you, Elizabeth, for your nice introduction. I'm delighted to be able to talk to you all, and many thanks to the organizers for inviting me. I'm just so sorry that this has to be done by this terrible vehicle of Zoom, and that we can't all be together. It's so much better when we can all be in person and then actually talk to one another and so on. Anyway, with that said, as you can see, this is a very grandiose title covering a very broad spectrum of questions and problems. Because of that, I'm going to, the talk will be at sort of, 100,000 meters. So a lot of it will be impressionistic. Some will be a little bit superficial. I won't go down very deeply into some of these things. And I will keep it non-technical. There'll be a few little equations, but mostly it's non-technical. And the main point of this is to present ideas and a way of thinking, maybe a complementary, a different way of thinking than is normally presented. And I'm going to begin with a quote from one of the great scientists of the 20th century, John von Neumann, without whom you wouldn't be having this Congress, because von Neumann was one of the great architects of modern computation and of modern computers. He sort of set the framework. He's the father, really, of modern computation. And here's a remark that he made in 1953, which we hope doesn't come true, but maybe. Oh, let's see. Oh, I hope this goes forward. And there we go. He says, the ever-accelerating progress of technology gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs, as we know them, could not continue. And that's going to be a theme throughout this talk, and I'm going to come back to it at the end. But I'm going to show you just something you're probably all very familiar with, an approaching singularity, so to speak, and that is just the world population. And here it is over the last 10,000 years. So beginning from when we started emerging from being hunter-gatherers to forming communities, eventually leading to cities, and then all the marvelous things that we all participate in now. And what you can see is what you're very familiar with. There's very slow growth for a long period of time. And then beginning around about 200 years ago, the Industrial Revolution, it took way up. It's gone almost straight up. That's signal of potentially some singularity. And just to give you a broader reflection of that, here are, you won't be able to absorb all of these, but here are just a bunch of metrics, some socioeconomic, some sort of material and physical, of the kinds of things that have been going on since the Industrial Revolution, from about 1800 onwards, from when we discovered fossil fuels and how to exploit them, and invented capitalism and free markets and so on, which have been enormously successful and led to this extraordinary, faster than exponential growth. And so the first point to emphasize is that in addition to living in an exponentially expanding universe, one of the things that we're often not quite so conscious of, ironically, is that we live in an exponentially expanding socioeconomic universe right here on the planet. Everything is actually expanding at a faster than exponential rate. And the question is, what is that going to lead to? And I want to give some understanding and explanation of that. So to, again, illustrate that, this you can barely see, but it's my estimate of what a photograph taken by a NASA satellite would have looked like in the year I was born, which happens to be 1940. And here's what it looks like today. And what you can see in that short period of time, the Earth is literally lit up. In fact, it's actually burnt up because, of course, what you see there, you will recognize what that is. That is night lights from urban areas, from cities. And of course, all those night lights are being driven by the burning of fossil fuel. And so the planet is literally sort of burnt up in that period of time. And no wonder there's global warming and climate change. And just to give, again, a sense of scale to that, that corresponds, if you just average from now to mid-century, to urbanizing something like 1.5 million people every week, which is equivalent to adding an entire Mexico City every couple of months, or a city the size of San Francisco every 5 to 6 days. So it's quite extraordinary, and that's kind of the root of the multiple problems and challenges we're facing on the planet in the 21st century. So here's a picture of the planet. But of course, what I'm trying to say is this is the way you should think of the planet. It's sprouted all of this urbanism and all the kinds of things we participate in. So the future of our planet is intimately related to the future of our cities, and it begs for the development of an understanding, and therefore the development of, or a question, can you develop a predictive quantitative science of cities in order to really understand the future of the planet? And that's what this talk will to some extent be about. So here's a city. This is what one thinks of. One thinks of a city. One immediately thinks of, the buildings and the roads and all the various systems of transport systems and so on and so forth, the physicality of the city. But in fact, this is the least interesting part, because the really interesting part of a city is what all that is there for, and all that is there in order to facilitate, support, and encourage interactions between human beings via social networks. And this is really much better image of what a city is, or this is New York about 120 years ago, but just the fermenting of interactions between people in order to create ideas, to create wealth, and to improve quality of standard of living. And great cities have both formal places to encourage that, like lecture theaters and universities and offices and sports stadiums and so on, to bring people together to interact, but also informal places like this or coffee houses, in order for people to come together, create ideas. And of course, what's going on here, all of the ideas that are created typically in this situation are not very interesting to anybody else. But what's amazing is that dynamic occasionally produces something like the theory of relativity or quantum mechanics, or it produces an Amazon or a Google, et cetera, et cetera. So that's what a city is for. That's what it does. It's probably the greatest machine we've invented as human beings, as social human beings. And it's there in order, as I say, to facilitate social interaction, in order to create wealth, knowledge, innovation, ideas, to increase standards of quality of life for everyone. And that's great. It's been enormously successful in doing so. But it comes at a price. We pay a price, and that price is it can be put succinctly in terms of the fact that you inevitably, and therefore unintentionally, also create entropy. The second law of thermodynamics is the most fundamental law of science. That is, if you create order in a system, then inevitably you also have to pay a price by creating some disorder. And so we're very familiar with this. We create both social and physical entropy, and you're familiar in one form or another with these kinds of things. This is what life is like, whether you like it or not. It may not be specifically these things, but this is the kinds of things that we have to be dealing with as a result of the great successes of producing the kinds of society and standards of quality of life that we have. And so we worry that there'll be situations like this will eventually occur on the planet in the not too distant future. And of course, the way we've dealt with this, the way we've typically dealt with this, is that we take the big questions and we deconstruct them into small questions. And here I've just very arbitrarily, this is just some arbitrary laundry list, if you like, of various things that we need to think about. And what we typically do is put boxes around some of these. And then, of course, we don't just do that. We put boxes within the boxes and boxes within those boxes. And we focus more and more reducing problems to very small individual problems or components and work on those. And this reductionism has also been extremely successful. Almost all of science operates that way. But it also comes at a heavy price. And that heavy price is because it often fails, and almost always fails, to take into account the fact that even though we think of these as being autonomous and disconnected, they are in fact all interrelated and interconnected. And in fact, each one is not only connected, but each one is a highly complex, evolving adaptive system, and the whole is a complex adaptive systems of multiple complex adaptive systems. So it's a daunting question. And of course, we're very conscious of that during this pandemic, because who would have believed that the evolution of some arbitrary virus in Wuhan, China, would lead to the shortage of flour in the United States, or no football in Spain, et cetera, because those things seem completely disconnected. But in fact, of course, what we've recognized with the pandemic, that everything in some ways is connected, and it always has been. Of course, loosely connected, but sometimes that plays a very important point. So let's talk a little bit about cities first. So they are very much a complex adaptive system. And in the biggest way of thinking about it, they are, like all complex adaptive systems, the integration and tension between, on the one hand, their physicality as embodied in the energy and resources that need to support them, their metabolism, so to speak, and their physicality in terms of their infrastructure, that integrated with and in tension with the information exchange between, in this case, individuals composing of social networks. And of course, that's the thing, as I say, that interaction leads, of course, to all the wonderful things we have and all the problems we have. So thinking of the word complex systems, I want to give you one quote from Stephen Hawking in an interview at the turn of the millennium, when he was asked the following question. Some say that while the 20th century was the century of physics, we're now entering the century of biology. What do you think of this? And surprisingly, Stephen Hawking responded, I think the next century will be the century of complexity. And indeed, I do too. And so the question is, can we actually have a science of complexity? Can there be some analog to Newton's laws of these kinds of systems? Almost the answer to that, I believe, is almost certainly not. There isn't some analog to that. That is, these systems are continually adapting and evolving. They contain enormous numbers of components. They have multiple levels. There are emergent laws within them, and so on and so forth. So almost certainly not. On the other hand, it doesn't mean that you can't do something quantitative and computational with them in a much more what we call coarse-grained way. So the idea is, could there be emergent laws that are sort of coarse-grained about average quantities and somewhat more statistical and more probabilistic in terms of the way we sort of start to address some of these questions? And that's sort of the paradigm, the framework in which I'm going to be effectively talking. Now, the first thing you realize about these systems is that a very powerful framework of thinking about them is to recognize that they are indeed all in some way or another sustained by networks. And you're very familiar with those. We've already sort of intimated them. Cities, of course, are network systems in terms of the roads, the electrical lines, the water lines, the gas lines, and so on and so forth. And various transport systems, and they're supplied, of course, by networks. And indeed, I just want to point out one thing. So here's the network just of the roads of the United States, the main highways of the United States. It looks like some sort of jumbled mess, like sort of loose spaghetti. But in fact, underlying that sort of mess are regularities. And I want to show you that by showing you this picture. This is all of the traffic in 1 year leaving Laredo, Texas, just arbitrarily chosen. And what you see is when you plot it this way, and the thickness of those lines, those red lines, are a representation of the volume. And what you see, it looks like something much more regular, a sort of fractal-like self-similar structure that's evolving that actually doesn't look so different than what's going on inside you and keeping you alive. And in fact, they aren't so different. They're actually quite similar. The major difference being that you're three-dimensional and this is two-dimensional. But there you are. That's how you stay alive, so to speak, your cardiovascular system. But of course, biology is replete, is dominated by networks. Your brain, this is just that same circulatory system supporting your brain, but your brain itself is like that. This is the white to gray matter in your brain, the computational part versus the sort of infrastructure part. And what you see, it also looks like a branching network. And your lungs and a tree is like that, and so on. So we could show lots of these. This is a little microbe that happens to live inside elephants, and so on. And this is down at the intracellular level. Cells have networks in them, and inside cells of mitochondria, they have networks. So there's networks at all levels of biology, from the microscopic all the way up to the ecological. And some work that I was heavily involved in the last many years is trying to understand these networks. And the idea was, can you have a general theory of these networks in this coarse-grained fashion? And so here were some proposals for some underlying principles for the generic structure of these networks, no matter what the specific engineering of those networks were, whether it was our cardiovascular system or a tree. The idea was these constraints should be operable. And they're all thought of as being derivative of the Darwinian theory of evolution and natural selection. So the first idea is these networks have to go everywhere within the system. So, for example, your circulatory system has to feed all cells in your body. That's called space filling, technically. And you have to put that into mathematics. The second is, which is called number 3 here, is the last branch of the network don't change when you change the size of the system. So that, for example, a mouse, a human being, and a blue whale, even though they're hugely different in size, the terminal units of the network, the capillaries, or the size of their cells, basically do not change. That is, natural selection, when it evolved new species, did not reinvent the fundamental units. It built up from them in the same way that we have sort of fundamental units of computers and computation and so on. And the last is, which I call number 4 here, which is the most powerful, is that the whole process of natural selection, the continuous feedback and the continuous drive towards the selection of the fittest, leads towards a kind of optimization, so that the organisms that have evolved have optimized something. So I'll just give you an example. So the system that we all share as mammals, that is, every mammal that has ever existed on this planet shares the same kind of cardiovascular system. And the one that is evolved is the one that minimizes the amount of energy your heart has to do in order to pump blood through the circulatory system to feed the cells. So in other words, it's a kind of minimization principle, and that's a very powerful one, and all of physics operates from optimization, minimization, or maximization principles. And so this is postulating that such a principle operates within biology, and that so that you devote the minimum amount of energy possible to staying alive, that is by sending blood through your circulatory system, in order to maximize the amount of energy you can devote to sex and reproduction and the rearing of children and passing on your genes. So that's the idea. So here they are stated in English. I should have said at the beginning, I do apologize that I have to give this talk in English. My Spanish is terrible, and I do hope you can follow it. Here they are, and all of these have to be put into mathematics. Now, that's not what this talk is going to be about. You have to take my word that you can put these into mathematics and solve all the equations. And here's something amazing that occurs from them, is that when you calculate something as fundamental as metabolic rate, that is how much energy does this system need to keep it alive per second, then that's called the metabolic rate. If you, here's the prediction. The prediction is that if you plot it logarithmically, that is going up by factors of 10, as you can see on the vertical axis and on the horizontal axis, going up by factors of 10 versus the size of the system, then it predicts this straight line. That's what all that, putting that into mathematics predicts that straight line. And here's the simple mathematical equation. It says this thing scales as the mass to the 3/4 power. This line is exactly drawn in as 3/4. And that's what the data supports. That's called sublinear. So that's what it was. That's linear. That's what it would be if you doubled the size. You needed twice as much energy, which is maybe what you would naively have thought. You have twice as many cells. You would think doubling the size of an organism, you would need twice as much energy. No, you actually only need, roughly speaking, 75% as much. There is an extraordinary systematic savings every time you double, saving of 25%. That's called economy of scale. And the fact that this exponent here is less than 1 is called sublinear. So that's crucial. And that permeates all of life. And I could show you the metabolic rate for the rest of the biosphere, and they all satisfy the same law because, from this viewpoint, they are all controlled by the mathematics and topology of the networks. So here they are. Here's some other things. This is for different kinds. This is for single cells and for cold-blooded organisms and so on. And here it is going all the way down through bacteria, so-called unicells up here, all the way down to the complex molecules that keep you alive. And just to show you, you can calculate everything with this, and you don't have time to really absorb this, but these are all the kinds of things you can calculate with this theory. And I show you the predicted value versus the observed, and the theory agrees, or the data agrees extraordinarily well with the theory. And similarly, it is with the respiratory system, your lung system, and here it is for trees. You do the same thing for trees. And this is extremely important because, as I said earlier, the trees, of course, are a different engineered system. They're a bunch of fibers joined together like an electrical cable, whereas you're a bunch of tubes that are joined together, yet the same principles evolve. And again, you don't have time, as I say, to look at this carefully, but you can see that the predicted and the observed agree extraordinarily well. So you can even extend it to communities of trees, so a forest. And again, here it is, there's a bunch of equations, and the forest recapitulates the individual tree, and again, you get very good agreement. And just to show you, here's the metabolic rate of plants, and this is the best fit, 0.78. Prediction is 3/4 for this line, and it's very close. Okay, so I'm going to I'm afraid I'm going to show a little bit of mathematics here, a very teeny bit, that that's what I said, that's what the prediction is, and that's what the data gives, that this slope is 3/4. And, but that means that the metabolic rate of a unit mass of an individual cell is decreasing in size. That's the economy of scale, and it decreases with mass to the 1/4. So it decreases in a systematic way. And so that gives rise to a very surprising prediction. So here I've just drawn a little cartoon by hand of the prediction. This is actually log of the metabolic rate of a cell versus log of the mass. And here's the prediction. This is what I just said. It decreases with a slope of 1/4. But what it says is that that's all because of the network. So if I remove the network, or if I take a cell out of a body in vivo and put it into a little dish and let it operate on its own, so I relieve it of the network, then it says that the same cell from different organisms behaving differently in different organisms all migrate to the same value. That's the prediction, and there's the data. You see, it's pretty good, and it tells you the value of that. And so that's a very nice confirmation of the theory. So here we have this systematic economy of scale covering the whole spectrum of life. You need less the bigger you are in a systematic, predictable way. And the last thing I just want to emphasize is that these scaling laws can be applied and can be calculated across all physiological and life history events across the entire spectrum of life. And they typically all have exponents. That is, the slope of the graph is typically a simple multiple of 1/4. The number 4 plays a fundamental role, and that is derived from the theory. So I'll leave that out, but so I just show you some of the other data in agreement with that. I'll just flash through it. Here's something mundane like heart rate decreasing with a slope of 1/4. Here's the radius of your aorta. That's the first tube coming out of the heart. You scale in the same way as a tree trunk. It's the same way, and the predicted is that that slope should be 3/8, which is what it is. And here's genome length. There's more scatter, more variance here. The slope of this is predicted to be 1/4. And here's growth rate over 20 orders of magnitude for plants, predicted to be 3/4, and so on. Here's your brain, your very self, and that slope is about 5/4. So these are sort of amazing. Here's one thing, the last two things I'm going to talk about in biology. One is lifespan, how long you live. That is predicted to be 1/4, to increase with a 1/4 power. Now, why is that? Let me just say one word about that. I said the bigger you are, the less energy is needed to support a cell, the bigger you are in a systematic way given by these 1/4 power scaling laws. Therefore, the cells in your body, the bigger you are working less hard, therefore less damage is done, therefore you live longer. There's less wear and tear, less damage, you live longer, and indeed, from that you can predict that lifespan increases as mass to the 1/4, which is what it does. But the point I want to emphasize here is I showed you that the same theory shows that heart rate decreases with that 1/4. And if you multiply these together, the increase of lifespan is exactly canceled by the decrease of heart rates, so that heart rate times lifespan doesn't change with size. But what is heart rate times lifespan? That is the number of heartbeats in a lifetime. And that is, so the prediction is that that should be the same across all mammals. So even though a shrew or a mouse lives for 1 to 2 years and a whale lives for 125 years, the number of times their heart beats should be the same. And there's the data showing it. So there's this kind of amazing picture that emerges that if you look through the right lens, actually, all these animals are sort of living in the same way. Their life histories are the same, and you just got to rescale appropriately. And so that begs the question, do they experience life in pretty much the same way, even though, as I say, some live for just 2 to 3 years and some live for over 100 years. So the last thing I'm going to do is growth about organisms. And so you've all done it. You've all scaled up. And we know how that works. You eat, you metabolize that energy, you send that energy through the networks. That energy gets apportioned on the one hand to maintaining cells, that is repairing damage or replacing ones that have died, and then adding new cells. And you can put that into mathematics. I hate to do it, but I wrote an equation for it for those that are mathematically inclined. And you can write that down here, just to put it into English. Here's the metabolic rate, gets a portion between the number of cells times the metabolic rate of each cell, times the energy needed to create a cell, times the rate at which you create them. And you can then use that to solve an equation and derive how animals grow with time, how they, their growth curve. And here's the solution to that equation. That's that solid line, and there's the data. It's extraordinarily good. This happens to be the best, one reason I'm showing it. But it's the point I want to emphasize. The fact that you grow quickly and then stop is guaranteed by the equations, and it's guaranteed because of the economy of scale, the sublinear scaling of metabolic rate, because metabolic rate scales slower than linearly, but the accretion, the increase of biomass is growing linearly. So the supply cannot keep up with the demand, and you stop eventually. So that's what gives rise to this bending over and the cessation of growth. And here's just some other animals. You can do it for, there's a couple of, there's a couple of mammals, there's a fish, there's a bird. And then because this is a universal theory with universal parameters, that is going back to this equation, these parameters in this, like the energy needed to create a cell, the metabolic rate of a cell, and so on. These are universal parameters. You can rescale, as I said a moment ago, so that everybody appears to be growing in the same way. You can derive, you can calculate what that curve is, and you can see it's pretty good. I'm not going to go into the details of what you have to plot, but the theory tells you how to plot it so that everybody look through the right lens grows in the same way. So you can also apply this to cancer. I'm not going to belabor it. Cancer is like you, and here's just data showing that the growth of cancer follows a similar curve. So in summary of the biological part of this talk, we have these extraordinary systematic scaling laws that cover the entire spectrum of life. They express an economy of scale. The bigger you are, the less you need per capita, so to speak. The pace of life systematically slows down the bigger you are. And growth is sigmoidal, which means that you stop growing, reaching a stable size of maturity, and then you die. And the whole network theory is able to explain this and explain it quantitatively. And so now I'm going to take it over to cities. You can do it for companies. I'm not going to talk about that in this talk, but you can ask the question, can we apply the same thing to cities and get back to this question of the growth of cities and sustainability questions with these ideas in mind. So first of all, the first question is, are cities scale versions of each other? Are they like these animals? So we just saw that even though a whale, a giraffe, an elephant, a human being, and a mouse look completely different, and they have different environments. We walk on two legs, whales live in the ocean, giraffes have long necks. At the 80–90% level in this coarse-grained way, they're actually scaled versions of one another in terms of anything that you can measure. Is that the same for cities? So I'm afraid I have to talk in terms of the United States, but is New York a scaled up Los Angeles, which is a scaled up Chicago, even though they're quite different and they look different? So the question is, are there hidden laws of city, just as we just saw hidden laws of biology? And we just, and I've already emphasized that cities are networks, much like biology. And so not surprisingly, you can derive such scaling laws, and here they are. This is for the infrastructure part of cities. This is for something mundane, and the gas stations, the petrol stations, as a function of city size, plotted logarithmically, just as we did in biology. And for population, I've used, for the size of a city, I've used population. And what you see is, again, there's very good evidence of scaling, and they scale sublinearly, much like biology. The dotted line there is linear. there. So the bigger you are, the less gas stations you need per capita in a systematic way. Not only that, this is just 4 European countries, and you can see they scale pretty much in the same way. The only difference with biology is that instead of having a slope of 0.75, the slope of these is close to 0.85. So instead of a 25% savings on the average with a doubling of each city, you have a 50% savings. So that's interesting. What is more interesting is that this is true across the globe. Everywhere you look, if you look at petrol stations across the globe, they in different countries, they satisfy the same scaling law. But even more powerful is that's true of all infrastructure. It's not just petrol stations, it's the length of the roads, the length of the electrical lines, the water lines, et cetera, et cetera. And we've looked at data in Asia, China, Japan. We've looked across Latin America, all the way from Chile to Brazil and Mexico, and in Europe, as you can see here, and so on. And wherever we can find data, it's the same. No matter what the infrastructure is, there's the same scaling law, very much reminiscent of biology. However, I said earlier in my introduction that this is the less interesting part of a city. The really interesting part of a city is social networks. These, where each node here is a person, and those lines are the connections to their friends, so to speak. And this is what a city is, but a city is much more than that, because that social network has to be tied to place, has to be tied to the infrastructure, and there's a symbolic version of it. Not only that, social networks have built into them modularity. We have families and groups and divisions and so on, and they have a kind of regular structure. So that this is, again, just summarizing this, that picture in the middle, which I showed earlier, is the interface between the infrastructural networks on the top and the social networks at the bottom. And a crucial aspect of those social networks is that A talks to B, B talks to C, C talks back to A, and they build on each other. That is a positive feedback mechanism. They build on each other and they create new things. That's the creation of ideas. That leads to innovation, leads to wealth, leads to the theory of relativity, leads to Amazon, and leads to all the marvelous things that we have. And it is this dynamic. And so this leads to, instead of sublinear scaling, the bigger you are, the less you have per capita. This positive feedback mechanism in social networks leads to something we call superlinear scaling. The bigger you are, the more you have per capita. And instead of the slowing down of the pace of life, you have the increasing pace of life. So it's a complement to what we had before. And we have these network principles, which are quite similar to what we had in biology, that they also have to be space filling. Social networks have to go everywhere. These infrastructural networks have to feed everybody. Everybody has to be connected. The terminal units are, roughly speaking, invariant. Houses, dwellings are sort of roughly the same. But then you have the question of what is it that cities are optimizing? Are they optimizing things like minimizing travel time? Did they evolve to minimize travel time to get from A to B? Or did they maximize social interaction so that you maximize the amount of interactions between people and therefore create more wealth and innovate? So that's one of the questions, but you could use all this, put this into a mathematical framework from which you, again, get the same kind of results as before. These power laws, so-called power laws, they're symbolically down at the bottom there, and these kind of fractal-like structures that we talked about earlier, and to recognize that all socioeconomic quantities depend upon the interaction between people, so they depend upon the number of interactions, the so to speak, the metrics that describe a city depend upon the number of interactions that are occurring between people, and they scale as an exponent, this superlinear, bigger than 1 with 1.15. This sort of 15% added every time you double. So what it says that on the average, as you increase the size of the city, the number of interactions increases relatively slowly as n to the 0.15. And so all socioeconomic quantities increase with this 1.15, and I'm just going to show you some data. This happens to be for the United States. On the left are wages, on the right are so-called super creative people. That's people like yourselves. People are professional people. And you can see the slopes of those betas written up there are close to this 1.15. Here's innovation. This is the number of patents as a function of city size. And you can see very good evidence of scaling. I forgot to write it in. The slope of this is actually closer to 1.2, but again, around that value of 1.15. This is how innovative a city is. And you can see it's continually increasing. The bigger the city, the more innovative it is because it's having more social interactions. Crime is another innovative phenomenon. Again, it's about 1.2. Greater crime, the bigger the city. This happens to be in Japan. And then other things like police protection and so on. All those, you can see the numbers hover around that 1.15. Here's another one. This is actually 1.15. Restaurants in the Netherlands and so on. So here's to put it in English so we all understand what it says. The good, the bad, and the ugly come together. If you double the size of a city or look at a city twice the size of another within an urban system, then systematically you save about 15% on all infrastructure, and at the same time you gain 15% on all the good things: income, wealth, ideas, patents, into education, creative people, but also all the bad things. Similarly, crime, social and disease, and so on, and pandemics, flu, all by about 15%. So that, just to give you an example, if you look at a city of 10 million, it will have double the number of COVID cases in half the time a city of 100,000 will, and have 200 times as many cases, even though it's only 100 times bigger. So to put it slightly differently, very bad to be in a big city during a pandemic, much better to be in a small town. On the other hand, in terms of the buzz of life, the access to more culture, more ideas, greater wealth, higher salaries, more jobs, more opportunities, much better to be in a big city. So here's a test of the theory. I've just put a panel of half a dozen metrics from across the globe. And you can see by eye, they all scale in the same way because they're all connected, because they all come from social networks. They all derive from the same kinds of social networks. And we can test that. And this is what was done with friends from MIT. We got billions and billions of phone calls, mobile phone calls between people, and analyzed them to measure their social connectivity. And what you can see is that it scales as predicted in the same way as all those social networks. And the two colors there correspond, in this particular case, to the United Kingdom and to Portugal. So that's very satisfying. And one of the big questions is, what happens when we interact in this horrible way that we're interacting now, where I can't see anybody, we don't smell each other, we don't touch each other, we're not in the same place, but we do this. How does this change things? So how does the whole internet revolution and speeded up by the pandemic change things? And I don't know whether this is relevant, but we did a little bit of analysis on some internet platforms. Here's subreddit on the top left, and here's Wikipedia on the bottom there. And the slope of these, as you can see, one is the comments for subreddit, and the other one is the number of edits on Wikipedia. So they scale with the same way as do cities. I don't know whether that's meaningful, but this is a big open area now, I think, for investigation and research. So I'm going to finish off quickly now by talking briefly about growth. It's the same paradigm, the same idea that we have for biology. We have something now, though, we have to generalize the idea of metabolic rate, have a social metabolic rate, all the various things that go into social life, and that gets apportioned between maintenance, repairing all the infrastructure, the buildings and the roads, etc., but also repairing people. You have to repair people, you have doctors and hospitals, so that's maintenance. And then you grow new stuff, you grow new infrastructure, you develop new areas, but you also grow new people. And so you have to put that into an equation. It's incredibly complicated. Obviously, this is extraordinarily complicated, and I've written it again for those mathematically inclined, symbolically up there, that the sum of everything has to be apportioned between those that contribute to the maintenance and those that contribute to the growth. And you can put this into equation. Now, the thing that makes this doable, that makes this solvable, is the idea that underlying all this is the same social network with the same scaling laws. So when you do that, you can write the equation and solve it. I'm not going to go through it. I just flash it on so you can see it. The only point here, and you don't have to know any mathematics here, is that the solution depends upon the exponent in those graphs. It was the 3/4 in biology. It's the 1.15 in social networks. And it changes this from being a positive number, 1 minus 3/4 is positive for biology, to being a negative number, 1 minus 1.5 for social systems. And that completely changes everything, even though it's the same equation. So the character of the solution changes dramatically from being like this for biology, where you grow quickly and then you stop and you remain stable. And this plays a crucial role in the sustainability and stability of the biosphere. That's why it's been around. One of the reasons it's been around for more than 1 billion years. However, this is a very bad paradigm for, this would be considered a very bad growth curve for economies and businesses and so on, because stop growing. And the paradigm that we invented with the Industrial Revolution and open-ended markets is open-ended growth. And indeed, one of the nice things about this theory is that the superlinear scaling derived from positive feedback in social networks leads by that equation to unbounded growth, which is what we see. And here I've just shown a cartoon version of it. It leads to, in fact, faster than exponential growth. So it's very satisfying, and it's a very self-consistent theory, and it agrees well with data. However, there's a price to pay, like everything else, and that price to pay is indicated by this dotted line, which is called a finite time singularity, because one of the, I'm going to go back, I'm sorry, one of the consequences of that equation, that solution at the bottom, where beta is bigger than 1, which is what we have, that gives rise to this open-ended growth, is that that growth goes infinite in a finite time, which is crazy. That is that you would have the GDP or the number of AIDS cases or the wages would go infinite in a finite time, which is crazy. And the theory tells you what happens. In fact, it tells you can't do that. What will happen is the system will collapse. And so that's very bad. And the question is, how do you avoid that? And this is now leading up to the thing I started with, the von Neumann quote. So here I'm going to go through just a simple exercise, a simple cartoon exercise. Here's some socioeconomic metric. It's growing open-endedly, super exponentially. It would hit that singularity and collapse. So it tells you what you have to do, because you realize that you've been growing within a given paradigm. Whoops, I will finish very shortly. Sorry about that. I'm just finishing up. That you've discovered iron, you've discovered bronze, you discovered coal, you've invented computers, you've invented IT, whatever. A major paradigm that sort of sets the culture, the background for what everything else follows. So here's such an example. And so it says that if you would collapse if you continue with this. So it says, it suggests that in order to avoid the collapse, you make a paradigm shift, you make a new innovation. You've had computers, you invent laptops, then you invent IT, and you start over again. And you go on, but you would hit another singularity, and to avoid that, you have to make another innovation. So there's a kind of theorem that if you demand unbounded growth, you need continuous cycles of innovation or paradigm shift to set the clock, reinvent yourself, start over again in order to avoid collapse. However, That's great. That's what we've done. And I'll show you a little bit of data in a moment to finish off. But there's a price to pay, and that is that you have to do it faster and faster. The time between these innovations has to get shorter and shorter. And here's data. This is not mine, but you can see I found this on the web. So with the numbers in brackets are just his choice of some innovations. The numbers in brackets are the time to reach 10 million customers. They're a proxy for the speeding up of time. And if you take those numbers and you plot them, they agree with the theory that I just described. And here's another version of it. This is what's plotted here is on this axis is how long it took to evolve life. It took several billion years, and it happened on this axis several billion years ago, all the way down through all these things to the ones here that are things that we're familiar with, computers and so on. And it turns out, this is not my data, this is by a man named Kurzweil, but this theory predicts this curve. And here's another version of it, the same curve, if you put it into on logarithmic scale. So I'm going to miss this out because I've gone over a little bit longer. I'm just going to summarize what I said. This unbounded growth leads to a finite singularity and therefore collapse. And to avoid it, you have to innovate faster and faster in a systematic, predictable way. And this is part of the predicted accelerating pace of life. Life gets faster and faster, and we need to adapt faster and faster. And one of the challenges is we have the same brain and the same biology that we had when we started this 10,000 or 100,000 years ago. And it's sort of like Sisyphus, we're pushing the rock up the hill and it rolls down again, and you have to keep pushing it up. And the whole question is, to what extent is that sustainable? So I'm going to finish up now just with a couple of very minor things to emphasize this. Your biological metabolic rate, how much food you eat a day, the 2,000 food calories you eat a day is actually 100 watts, 90 watts. That's all you need to stay alive. You are remarkably efficient as a biological organism, but your social metabolic rate, if you live in the United States, that is all the things I need to do the things I do, the house I have, the car, the transport, and so on. That is 100 times bigger. We're 11,000 watts. And so this graph I showed earlier, effectively, the metabolic rate versus size, where we fit exactly where we should on the graph, is 100 watts. And we fit with everything else. We co-evolve with everything else. Now we're up here, and we violated the scaling laws by having discovered language, evolved cities, and done the things we've done. And we can ask, how big an organism are we when we're social man? We're equivalent to a 30,000 kilogram gorilla, or each one of us is equivalent to about a dozen elephants. So that's the singularity, and that's what von Neumann talked about. And I hope I've given you some insight into it. I just will flash this on. These are many of the people I've collaborated with. Most of them are young people in different fields to do this. They're wonderful people. And the last thing I'm going to do is shamelessly advertise that if you want to read about this, I wrote a book. This is the English version that has it all in it. No equations in this book, unlike this talk. So I'm sorry I went on a little bit too long, and I apologize. And if there's time, I'm happy to take any questions if anyone's interested.
Thank you so much for this amazing lecture, Doctor. I think that is a little bit weird to talk using a camera and a computer. It would be better if we were in person, face to face.
Yeah, exactly.
But now it's time to questions. I don't know if anyone in the public has questions. Don't be shy. Okay. Well, I'm working in different topics, but it's very interesting the things that you have taught in this lecture. And for example, I'm working in my laboratory, I'm working with networks, with neural networks, but also only for simulations. And I see that for the last example with the last example with the spikes, it's very illustrative. Dr. Yama, you can open your microphone if you want to ask something to Dr. West.
Yes, but did you finish your question, Lisa? Sorry?
Only it was a commentary. A comment.
Okay. Well, thank you very much. First of all, thank you, Professor Geoffrey, for this enlightening talk. It's a relief to know somehow there are some constants in life, so it's much better. And my question is regarding the quarter in which cell with neighbors decreases its needs. Do you think it has to do with the number of neighbors it's living within? Because it's easy to think there are 4 neighbors, so maybe that is the decrease of the resources it needs.
I'm sorry, I missed the beginning of your question. I'm really sorry. There was some background noise. Could you just start the beginning of the question?
Oh yes, it has to do with the cell, with neighbors.
Cell, yes.
So you mentioned it has 1/4 of the energy needed when it's living in society or with other neighbors. So does it have to do with the number of neighbors it has? Because it's easy to think there are 4 neighbors, yeah. 1, 2, 3, 4. So these magical numbers, do you think it has to do with this?
No. It's very important, of course, to have a model of the local environment of the cell, clearly, and how it interacts with others, and so and how it's packed, how they're packed together, and so forth. But what this comes from, this is this 1/4 comes from 2 things that are for the total metabolic rate. It comes from 2 things. One is that the network has to fill all space. And so the 4, first of all, that 4, let's call it 4 rather than 1/4. The 4 is actually, 3 of the 4 is to do with 3-dimensionality of space. And the +1 is to do with the fractal nature, this branching nature, and the optimization of that branching nature as delivery is done to the cells. So it's to do with delivery to the cells and how that's controlled by the overall network more than the interaction. So it's completely backwards to the normal way we think. Namely, what we think of is what you said in a way. You start with cells, and how do they pack together? How do they interact together? And then we build up the organism. So, the properties of the total organism is somehow a sum total properties of interacting cells. This says, yes, there is that, but then there's a kind of back reaction, which is that the system as a whole is controlling the cell, because of those networks are controlling the cell in terms of the rate. It deregulates the cell, it slows it down the bigger the network. And it's a little like, I can only give, this is maybe not a very good example, but it's like, you know, if I'm rich and I own a fancy Porsche sports car that can do, you know, 250 kilometers an hour, and I live in the middle of, well, even Mexico City. I live right in the middle of Mexico City, and I start that next, you know, I bought this car and I go out the next morning, and I tried to drive that car in the middle of Mexico City. I go at 20 kilometers an hour. That's the fastest I can probably go, because the network, which is called Mexico City, is controlling me. But if I go out in the middle of the night outside of Mexico City, and I'm no longer, I can go, and the police are not there, I can go 250 kilometers an hour when I'm free of the network. So it's a little bit, it's like that. So that's the control. So it's counterintuitive, actually, this. And I think it has an important lesson that the system plays an important role on the individual. Even though the individual is the constituent of the system. The system is made of these individuals. So it's what I tried to emphasize, or at least mention in the beginning, about the very nature of a complex adaptive system. That it's sort of this continuum from the reductionistic individual all the way to the system size. And it's crucial to take that into account. And by the way, I think that's one of the problems with a lot of biomedicine, is that we don't take into account the systemic nature of many of the problems we're dealing with. Anyway, that's a separate comment. But that's a very good question. It's a very important question.
Thank you. It's been a pleasure.
Thank you, Dr. Ram. Is there another question? I think no. I want to ask you, Doctor, if you can ask a question to our public. We are going to make a raffle, and we are going to give a T-shirt to who answers the question. Sorry. In Spanish, I will switch in Spanish. Sorry. Bueno, vamos a hacer una rifa de una playera. Esperamos que el doctor West haga una pregunta y el que responda primero va a ganar la playera. So if you can ask something to our public, Dr. West, please.
I'm happy to answer it. Yes, sure.
I wanted that you ask a question to our public. Do they win a T-shirt? Yeah.
I'm not sure I'm understanding you. Is there a question there?
Sorry, I'm going to try to reformulate my question. My petition is a petition that if you can do a question to our public in order that they can they win a T-shirt.
They can what?
A T-shirt.
Oh, I ask a question. Then I ask a question.
Sorry, my English is a little
They
horrible.
answer it. Oh my God. Well, I don't know. It's really not it's a funny question in a way where they can answer it. What do you see the future for Mexico City?
Thank you, Doctor.
That's yes, that's very good. Whoever answered that, that's really good.
So Dr. Ram won the issue. Thank you.
I like the answer. I like the answer.
Thank you very much, Dr. West. I'm sorry because I speak a little bit horrible, but we have a winner for this T-shirt.
Good. I've got someone. That's good.
And I think that's all because there is not questions for the public.
Okay.
Well, thank you so much to share.
Mr. Chimal have a question.
Yes, Dr. Chimal, you want to say something?
Yes, can I, well, I open my micro. I think it could be okay.
I hear you.
Dr. West, thank you very much for your interesting talk. And my question is that if these scaling laws, do you think that behave the same on Earth than, for example, in Mars? Depends on physical quantities? Or depends on other things, for example, the gravity or the atmosphere, or I don't know what else. What do you think about this?
Yes, that's a very interesting question. So if you plants, definitely it changes on if you were to go to Mars. If you could grow trees on Mars, they would be different. And a theory we can develop. We have a theory, and in that theory is something you just mentioned, namely that gravity, the acceleration due to gravity, occurs in those equations actually, because the infrastructure, so to speak, of a tree, that is the biomechanics of a tree, plays a crucial role in both not just the scaling laws of trees, but how the tree grows and its structure. So yes, that would be an intriguing thing to do, and it would be an intriguing thing to do even if you could, you could do it in space. Now, people have tried to grow things in space, and you can, but the trouble is there isn't enough. The size scale isn't big enough within the space station and so on. But eventually, presumably, people will be able to do experiments over much larger ranges of scale and really test the effect of external parameters on plants and organisms. There's obviously some things to do with that. I mean, gravity is a crucial piece of it. It's maybe the biggest piece of it. Now, I think one of the interesting questions that is kind of science fiction question is, if societies developed on other planets or other galaxies, would they have similar kinds of structures to our societies? I mean, if these results depend upon very general principles of social networks, and but it depends on what you want to optimize. I mean, it may be that you could have a society where you don't optimize on the number of interactions. Maybe that's not important for a different kind of evolutionary trajectory. But anyway, no, I think it's a very interesting question, because it brings up all kinds of speculative answers, and also it allows one to focus on what are the parameters, both internal and external, that are controlling this.
Thank you very much. I was thinking about this colonization of Mars, in which, for example, gravity is different, but also temperature is different. So I was thinking about these variables that Mars has different from the Earth.
Sure, absolutely. No, it's an interesting question. I've actually, much longer ago, maybe 10 years ago, I interacted with people at NASA about some of these questions. But it's come up, funnily enough, it's come up again recently, because people are now, just as you say, starting to take seriously, which I have mixed feelings about, colonization of Mars. What happens if you have, what are the parameters that control both social and physical behavior in a colony on a different planet? I've not got involved in that, but I was asked to be involved, and I didn't. But I did give some thought to it along the lines we just discussed.
A final point is there any book or any paper that you recommend to read for these things?
Well, the only thing, as I said, I try to advertise my book at the end. There's this book called Scale. I don't think there's the English version. It's translated into, I don't know, about 15 languages or more, maybe more. But I don't think there's a Spanish. Ironically, it's amazing. I don't think there's a Portuguese version, but there's not a Spanish version. I don't know. At least I don't think so. But there is an English, and the book. So the point about the book is that it's it does. I try to explain everything, and it's very much this kind of thing I talked about today. But it does it with no mathematics. But I do give references there, and you can look up the references if you want to pursue them in terms of the technicalities.
Thank you very much.
Pleasure.
Thank you, Dr. Shimal. Is there another question? I think there are no questions. So again, thank you very much for this lecture, Dr. West. And well, with this conference, we are finishing our congress. Then we are welcome to the closure to this event.
Thank you for inviting me. I enjoyed it. I'm just so sorry. I would love to have done it in person, to be there together.
It could be better.
Maybe another time.
Another time. Thank you so much.
Thank you. Bye.